So let's begin Poisson distribution. So Poisson distribution is nothing but the extension of binomial probability distribution. So why to use binomial distribution? So whenever we are doing the experiments in large number and we want to find the probability of any number of say event out of that large number of event or the trial, we always use, or we normally use, binomial probability distribution. And one more thing, the outcome should be 2 in number. So so the Poisson distribution is again extension, or it is derived from binomial probability distribution. So in binomial probability distribution, if this n is the number of trial, if this becomes very large means say infinity, and this p, this is the probability of getting success, becomes very small. So what happens in binomial? It was sometimes half and half, or 3/5, something like that. But if the probability of success is very small and the number of trials or the experiments I'm doing is very large in number, my binomial distribution changes to, or it modifies to, Poisson probability distribution. The formula for Poisson is this, where this R is the number of times we need success out of n. This n is very large. What is Z? Z is mean of Poisson distribution. It is calculated by this. Z is equal to n into p. And this e is the exponential. The value is 2.718. So that's all the theory for the Poisson distribution. Now let's take example. You have to decide whether the question is on Poisson or binomial. If you are unable to decide, you can solve it by any method. You will find that the probabilities are eventually equal, or they are close enough. So the question is, a manufacturer of pens knows that 2% of his product is defective. So what is the probability of defective piece? Is 2 upon 100, 0.02. Let's read further. If he sells pen in a box of 100 pens, so in one box there is 100 pens, and we don't know like this how many boxes we have, so it's like very large in number, and he guarantees that not more than 5 pens will be defective in a box. Find the probability that a box will fail to meet the guaranteed quality. So our success is to fail that manufacturer. That will be our success. So let's read the solution. Here n is 100, so we are discussing only for one box, but remember that there are a large number of such type of boxes. N is 100, 2% of product is defective, so P is the probability of success. In this question, our success is to prove that is to prove that manufacturer he is failing to fulfill his guaranteed quality, to give his guaranteed quality. So the probability of defective product pen is small p, so 2 upon 100, which is 0.02. That's very small. So this is the Poisson probability formula, where this Z is mean and n is 100. 100 is number of pins in that box, so 100 into p is 0.02, so which comes to, so mean for that data is 2, arithmetic mean. Now the manufacturer guarantees that not more than 5 pins will be defective. In order to fail, manufacturer number of pins to be defective are 6 pins, 7 pins, 8 pins, 10 pins, 99 pins, like this up to 100 pins. That is, the R should be greater or equal 6. So for this R, the guarantee of that manufacturer, he is going to fail. His guarantee is not meeting. So probability of guarantee fails is PR greater or equal 6. And we know this. P0 plus P1, P5, P6 up to this all is 1. Sum of all the probabilities is 1. But we are interested in P6, P7, P8, P9, P100. So sum of this. I'm not going to calculate P6, P7, P8, P9, P99, P100. So instead of solving all those probabilities, let's solve these 6 probabilities. P0, P1, P2, P3, P4, P5 up to P5 and subtract it from 1. So this is the statement, the equation we want. So I'm calculating P1, P2, P0, P1, P2, P3, P4, P5. These 6 probabilities I will find and subtract it from 1. So by using Poisson probability formula, so let's calculate P0. From that formula, Z raised to R E raised to minus Z. So Z is 2. So 2 raised to R is 0. So 2 raised to 0 and E raised to minus 2. So E is 2.718 raised to minus 2. So this term is everywhere in every probabilities. So you have to calculate it and keep it separately to write it in every probability. So how to calculate this? You will calculate 1 upon 2.718 raised to 2. So you can find this and divide it by 1. What you will get? You will get 0. So value for E raised to minus 2 is this. So use this every time in other probabilities. So what is P1? So this is the value of P0. P1 is 2 raised to 1 E raised to minus 2 upon 1 factorial, which comes this. So every time you will write this equal to this value. Like this, I have calculated all the probabilities. Use calculators for this. Add all these, subtract it from 1. So you will get this. So this is the Poisson probability that he will fail to fulfill the guarantee. Let's take the other important example. In this example, in this question, we have to fit a Poisson distribution. Fit a Poisson distribution to the following frequency data and compare the theoretical frequencies. So what is this? This is some observation. What is x is 0, 1, 2 and 3, and the practical the observations is 150, 154, 60 and 35. So these are the practical original data. What we are doing, we are attaching a probability row to this table, and we are writing the Poisson probability in that row. So let's write let's find mean for this frequency distribution. We know this formula very well. So I have multiplied the frequencies with their observation. So in the numerator, it's addition and multiplication. This is the sum of all frequencies. So the arithmetic mean for that frequency distribution is this. This is the arithmetic mean, which will be the mean for Poisson distribution also. So this is the Z. Let's recall Poisson distribution formula. Poisson probability formula. So PR is Z raised to R. This is the formula, E raised to minus Z upon R factorial. Z is 0.94. E is 2.718. You have to calculate this term. Use this every time. So it comes 0.39. So this is how I have calculated P0, P1, P2, P3. So these are the probabilities I have calculated. So these are the probabilities I have calculated for different values of x. So x 0, 1, 2, 3, these are the original frequencies, and this column, this row is the probability. This probability is Poisson probability. Therefore, this table is called Poisson probability distribution. Now we have to find the theoretical frequencies. Theoretical frequencies means what are the frequencies calculated by using this formula. What frequencies, what numbers they're going to give with that formula. So we know this formula, PR is equal to NR upon NS. That's the very basic formula of probability. We have to find this N of R. This N of R is the theoretical frequency, and N of S is the total number of observations in my data. So if we go back, we have to add all the frequencies to get the total number of observations in my table. So the addition gives me the total frequency is 399. So let's go down to the end of this solution. Okay, so N of S, the sample size is 399, and I am interested in finding this theoretical frequency NR, and this PR we have already calculated. So this row was the PR. Okay, so NR, we want to find NR. So NR is equal to PR, just cross multiply this with PR. So 399 multiplied with PR. So P of R. So calculate N0, N1, N2 and N3. So formula says that for x is equal to 0, the frequency is 155, but real observation says that it was 150. N1, P1 into 399, P1 is 0.36 into 399, 143, so it comes 143. So theoretical frequency is 143, but actual frequency is 154. Similarly, you can calculate N3, N2, it comes 67 and 62. So just remember the Poisson probability formula, this formula, and the binomial, also binomial probability. And this is all about probability distribution. Right now I'm not taking normal distribution. If you want, you can search, you can Google it. So these three topics in fact are important from exam point of view. You can search more examples on Poisson and binomial distribution for practice. Thank you.